Okay, we'll start with our formal definition of the limit. Okay, limit definition. Because we can't just keep going on this idea of close as a phrase. It's not mathematically rigorous enough. So we need a precise definition of what we mean by close. So down here, it says the limit of 2x minus 5 as x approaches 3. So to say that that's equal to L would mean that as x gets very close to 3, then this expression gets very close to L. Now, we could do a direct substitution to get things started. We can see that this should be a 1. Since when x is very near 3, this would be very near 6. Minus 5 would be very near to 1. So we're going to bet on that being our limit L1. Okay, now, epsilon delta definition says that the statement limit of f of x as x approaches a equals L means that for every epsilon positive value greater than 0, there exists delta greater than 0. I said greater than 0 here, epsilon, and greater than 0 here, delta. There exists a delta greater than 0 such that whenever we have this condition, then we must have this condition. Okay, so graphically, let me give you a little drawing of what this means to get a better idea conceptually what's happening here. Okay, now I just noticed on my diagram here that I have C here, and when I gave my definition up here, I was using an A as my limit point. It doesn't matter if it's an A or a C, but I could make this an A in here. That way we're more consistent. Now, this is graphically what's happened. This expression, x minus A less than delta greater than 0, if you open this up, now, first of all, this part here only tells us that x is not going to be equal to A. We're not concerned with x equal to A. That's what this tells us. So this part of it says x is not equal to A. This part says this, x minus A less than delta and greater than negative delta. Okay, which says that x is less than delta plus A and greater than A minus delta. Okay, so that's what's in here. Notice, here's A, and this point over here would be A plus delta, and this one here would be A minus delta. So x is in here somewhere along the x-axis. It's stuck in here. That's what it says. So if x is in there, somewhere between A plus delta and A minus delta, in other words, if this statement is true, and we don't really care what happens if it's right at A, we're not concerned. If this is true, then we'll have this true over here. As long as this is true, then this will be true up here. In other words, f of x minus L would be less than epsilon. And this statement is the same as saying that f of x, and I could run through it the way I did down here, is less than L plus epsilon and greater than L minus epsilon. In other words, that's inside of here, between here and here. So function would be stuck in there somewhere. For value of x, f of x would be in here. Okay, so we could kind of look at that. If x is in here, between here and here, excluding x equals a, we don't care if it's x equal a or not. It's not our concern. If that's true, then we'll have, let's see, we'll have our f of x in this band in here, someplace, guaranteed. If we can find a delta that will guarantee that this is true, whenever this is true, then the limit must be L. F of x, that limit must be L. That's what it says. So one other thing that you notice about this is that there could be a hole right here in the graph. In other words, f of x might be undefined and yet still have a limit. We saw that in our first example where we had that graph coming down. Let's see, I lost my video there, but we had that graph coming down. We saw that it was getting closer and closer to the 0.125. But right at that value, there was a hole there. We couldn't see it graphically, but it was there. It was undefined. So that can happen. We'll still have a limit. Okay, so that's just preliminary stuff. Now we're going to look at this particular example, how to use the epsilon delta definition to prove that your limit is actually what you think it is. Okay, so here we have what we think it is. We think it's 1, but we want to prove it using the epsilon delta definition. So this is how you go about that. Now, to prove that this is true, we would have to find a delta greater than 0 such that for every epsilon greater than 0, if x minus 3 is less than delta, then we would have 2x minus 5 minus 1 would be less than epsilon. No matter what epsilon is given as long as it's positive. So what we'll do is we'll start with this statement here. We are gonna try to take this algebraically and see what this implies in terms of this expression. So here's typically how we would do that. We start with this and try algebraically, this is an algebraic approach, try to visualize this expression. So and then from there we may be able to find what we need to set delta to make this happen. So let's try this. Start with this. I have a 2x minus 6. Pull out a 2. This is what we needed right here. So I can see that if I start with this expression and I make my delta no bigger than epsilon over 2. I can use a smaller number than that, but if I make it no bigger than that, in other words, choose delta as epsilon over 2 or smaller. Okay, so this would be the largest delta that I would use for this. If I chose it as epsilon over 2 or smaller, then I would be able to make this claim. And let's run through that and how that works. So if I start with this, will that imply, so here's my question, will that imply this? That's the question. If it does, then I've got my proof. Okay, then that's proving it. So I start with this. This is my choice of delta. Now I'm just going to see, I'm going to work with this portion here. And notice this will become a 2. You see the same way I got here, I'm going backwards. 2x minus 6. Okay. And pull out that 2. Oh, I'm sorry, I'm going backwards. I'm going to pull out the 2. I've got what I need here. Okay, so I have a 2x. I want to write this as minus 5 minus 1. So in other words, I can't just, I have to know where I'm going in order to get there. This isn't random. I know I'm trying to get to this statement right here. So if I'm going to do this algebraically, I have to keep an eye on that final form. So that's why I broke it this way. And I realized that is the final form. This is in the form f of x minus L is less than epsilon. So that's the proof. That is the delta that works. Okay. So that means that the limit must be 1 because I was able to find the delta dependent, which will normally depend on epsilon. Okay. In most limits, it'll depend on epsilon. I was able to find that delta to make this claim that this, if I have this, then I'll have this. Therefore, that limit must be the 1. And that's how you do the epsilon delta proofs.